One way of thinking about natural flood management is by slowing the flow, slowing the rate at which a flood peak travels downstream and reducing the height of that flood peak, spreading the amount of water out over a longer period of time and therefore reducing the maximum height of the flood peak that water reaches. That's really the mechanism by which we're reducing flood risk with natural flood management. And there are a number of principles that lie behind the concept of slowing the flow. Really what we're talking about is working on a catchment basis, so as far upstream as possible, by increasing the roughness, the hydraulic roughness. So we're talking about influencing the rate at which water travels over land and the rate at which it travels in the streams. And there are three different mechanisms. We can either provide and build physical barriers to the flood peak so that multiple structures in streams or on the floodplain that physically slow the rate at which the flood peak travels downstream, and then cumulatively you achieve the reduction in flood peak. Secondly, we can look at attenuating water, so that's creating temporary storage or pooling of water. We can use woody debris to push water onto a floodplain. We can create pools and hollows that we can divert water into where it will attenuate. It may well just be that we site our woody debris in stream in places where there's room to attenuate water behind. We can look at field bunds, intercepting surface drainage, overland flow and attenuating water where there are no streams and no water courses. The third mechanism we can look at is infiltration. So that's the rate at which water soaks away into the ground. We can either use the natural geology, the natural propensity of water to soak into the ground. We can deflect water out of channels in places where we know it will drain or soak away. We can create areas which will divert water back into groundwater by creating soakaways, for instance at the discharge end of a culvert. Another way of increasing infiltration is through tree planting. Studies have shown that planting trees in a targeted way can increase infiltration rates by about 60%. We won't always achieve that increase, but when the roots are being established, the act of planting takes place, then we know that we'll be increasing the rate at which water soaks away. Before putting in place practical implementation of natural flood management or slowing the flow, it's vital to ensure that you have the full support of locally elected officials, parish councillors, district county councillors, flood action groups, wildlife trusts, national trusts, local charities, land managers and farmers, landowners. There really is a wide community of people that have to be fully aware and informed and hopefully involved in the delivery of natural flood management. There needs to be an appreciation of how land management and water management need to change in the long term to deliver the reduction in flood peaks required.
I think one of the key things to understand before moving on to looking at interventions is the geology and the way that water moves through the catchment and whether or not your catchment is dominated by a permeable or impermeable surface geology. This catchment we're in is classic for the Cotswolds in that further downstream clay and Cotswold sands start to come into the surface geology, and so it becomes more impermeable. Here it's much more permeable surface geology dominated by bedrock and Cotswold brash. We know that if we can move water out of the channel, then it will start to infiltrate very quickly. And this is a really important feature of our attempts to slow the flow here, because we know that after a big rainfall event, when we're getting a lot of surface water coming through down that channel, it will also infiltrate away, and we take that whole tributary's flow out of the flood peak travelling downstream.
Trees and riparian woodland are one of our main sources of material for making structures. There are different types of structures, there are different uses for these structures, and the type of measure you're putting in place determines how to build them. We can use simple, large woody debris structures placed laterally across the channels to act as a physical barrier to slow the flow. We can use large woody debris to deflect water out of the channel so it can fill up a floodplain or an attenuation area. We can use pieces of timber to raise the bed level to deal with a process called incision, which is where streams have been devoid of any sort of obstacle, so the energy of the flow acts directly to cut the stream bed and makes it deeper, making it much more likely to act as a gutter or a drainage ditch. In most cases, in a stream, woody debris must allow base flow to continue unimpeded. So that's the normal flow under normal winter low flow conditions. That's to allow fish and other aquatic animals to move freely through the structures. It also means we get free movement of silt and sediment through the structures too.
This is what people would imagine if you talk about a woody debris leaky dam. It's very lateral, it's positioned in such a way to attenuate the maximum volume of water, which it's doing really nicely. So what's happened here, this log's been in place for a while now. The silt and the stone and the natural transport of bed material downstream has built up behind this, and it's raised the bed level by a good 1.5 feet, 2 feet. That's why we have the difference between the bed level downstream and upstream. So we've got this cascade as water's blocking up and it can't get underneath it. Raising the bed level means we get better connectivity between the stream channel and the floodplain, and it also means we get these features, these cascades, which cause scour and pooling, so we get a variety of deeper and shallower water.
Which is great for fish and other wildlife.
I'm standing on this, it looks like a fairly low-key structure, and it is low-key. You can see we're in a dry channel. There's no water flowing through here, and because we're in a dry channel for most of the year, it means that we can put the structure further down onto the ground, so we can completely block this dry channel, because we know it's only running at times when it's been raining very heavily, the groundwater is very high.
This looks like a dry area of the woodland floor, but in the middle of this is actually the course of the Sheepscombe Brook. It's ephemeral here, largely because the surface geology is very permeable, but this is in fact the floodplain of the Sheepscombe Brook, and under periods of intense rainfall we get flow. And what we've done is use these big poplar trees. We've laid them down to interrupt the flow, and what we want to do is to spread the whole flow out over the floodplain to give it time to infiltrate. The permeability of this ground is very high, but the permeability of the actual channel is low, so if we can knock the flow out of the channel, we increase the infiltration rates dramatically. We don't need to allow for base flow. So these structures can be hard onto the ground, they can have a bit of soil around them, so they're bedded down, impermeable structures. There's a key technical difference between here and the structures in parts of the stream which have permanent base flow.
And so looking upstream, we've got a classic kind of Cotswold escarpment gully formed by surface runoff from the fields above. So there are huge areas of arable fields and pasture fields above us, and some of the surface drainage, the overflow from those comes down, has eroded this gully. So we've done several things here, one of which has been to take as much wood as we can find and fill in this gully to slow the flow of water coming through the gully. And hopefully what will happen is, as material is eroded and cut, so stone and soil, it will build up behind this wood and start to fill this cutting section of the gully back in. So we're slowing the flow to reduce erosion, and we're also increasing infiltration.
It's important to understand that this is fairly new and experimental work to see if we can reduce erosion and slow the flow, but we'll be watching this very carefully. The choice of which trees to fell is clearly one that has to be made in close consultation with the landowner. Obviously, it's better if obtaining the timber can be tied in with some sort of felling or cropping or coppicing works, and normal kind of woodland management principles apply. But once you have your material, hopefully it's been obtained from very close by to the stream. There's a number of ways to move it into place. If you have good access and ground conditions allow, then having a tractor winch is clearly the easiest way of moving timber around. If you don't have a tractor winch or access is restricted, then you can use a turfer winch, a hand winch, which still provides you with a good degree of flexibility, and used in conjunction with pulleys, you can still obtain good structures. If you don't have a turfer winch, your options are pretty limited. You can drag them in place with hand calipers. Obviously, this limits the size of the timber you can use. Irrespective of which method you use, a good crowbar is an essential piece of kit. There's an infinite range of types of structures and forms that you could build. The choice at any particular site will be dependent upon a combination of landowner preference and what you're trying to achieve. Really, there are three main categories that we use. There's naturalistic or very natural structures, which are tree trunks felled into or just left as they lie in the stream. A semi-natural, semi-formed, where we maneuver tree trunks and logs into place, but still leaving it reasonably natural. And then there's very structured. These would be structures formed so it is absolutely obvious that they've been created as part of some scheme or project. Basic principles apply with all three of those types. So if there is a base flow in the stream, this should be allowed to continue unimpeded. The length of the logs and the tree trunks should be such that there's enough material extending over the riverbank or the stream bank to impede water trying to get around the structures at high flow. The decision about what fixings to use and how the structures will remain in place is one that should be taken before the works start or commence on a site. This is going to depend upon a combination of landowner preference, what the structures are trying to achieve. It may also be affected by the consenting of the structures, which may require fixings to keep parts of the structures in place. There are really four options available. Structures can be simply left unpinned, so it can be created, and then all of the timber, the logs and the trunks are left as they are, unfixed in any way. We can decide to pin using reinforced steel, which is drilled down through the structures, or we can pin with chestnut stakes. We can bury and excavate parts of the tree trunks into the bank to create a fixing, or we can use a system called pleaching, which is where tree trunks are partially cut and then folded over so there's still wood and bark attached to the stump, which will mean we create a living leaky system, which is attached to the ground by the roots of the tree, the hope being the tree will continue to grow laid down into the stream bed or in the channel. If pins and fixings are required, the aim is to create a complicated structure which is fixed not only to itself but to the ground. This will reduce the likelihood of floating off in high water or being moved by people who are investigating the structures.
This is the field at the base of the gullies we've just been through. In 2007 there was a great deal of flow coming through this area. When we checked on the LiDAR mapping, surface water flooding did indeed show that this area collects quite a lot of water, even though there's no watercourse. The top one here effectively protects the second bund, so collects soil and silt and takes some of the strength of flow out of the system. The bunds are formed by removing the topsoil and the turf, removing the subsoil, and then reshaping. These are capturing surface overland flow. So they're designed to be slightly permeable, but they are designed to attenuate quite a large volume of water. Each one of these bunds took a day with a 13-ton excavator to make. These have also been reseeded and then consolidated to prevent soil erosion from the crest of the bund. This is the second in the series of bunds, formed in the same way, so topsoil and turf removed, pushed over to one side, and then subsoil and clay reformed and reshaped across the whole length. So taking a couple of inches for about a couple of meters in front. So gentle scrape, bringing the clay back to form the bund. And again, these bunds are not dealing with flowing water in a stream situation, this is overland flow. So they're not built to the specification of flood banks, and they don't need to be built to that specification, which means they're much quicker, much cheaper to construct. What we don't want is water on the footpaths and the bridleways, because they act as conduits for fast flow. They convey water very quickly, and that water travels at high speed. It pulls out soil, it pulls out stones, and that soil and silt very quickly winds its way into the stream channel, causing pollution problems. So we want to keep that out. So that's why we've got these grips, these systems of channels that take the water off the track, and where we can slow it down and manage the water more effectively.
Culverts are a technique widely used by farmers and landowners to allow streams to travel under tracks. But rather than build a traditional culvert, we can add some modifications that slow the flow even more and allow us to attenuate or infiltrate more water. Simply adding a large catchment chamber to the inlet means that silt can gather and be regularly cleaned out. It also provides a small pool of water before the culvert becomes engaged. And then on the discharge point of the culvert, we've built these very large deep soakaways. We've excavated a big chamber, filled it full of clean stone, and the net result is that a lot of water coming through these culverts is discharged straight to groundwater rather than travelling through the surface flow system. Even though we're speeding the flow of water up underneath the track, ultimately we're slowing it down by the use of a soakaway. To further slow the flow, it's also possible to put brash and smaller woody debris in any of the kind of ephemeral channels that are downstream of the culverts. In situations like this, where you have overland drainage flow, bringing silt, soil and nutrients down into a watercourse, it can sometimes be possible to divert that flow overland so it completely infiltrates. In this case, it's to prevent the drainage flow from reaching the springs. In other cases, it may be to slow down the drainage flow before it reaches a watercourse. Like most activity on land or in the countryside or in streams, natural flood management will require a range of possible consents. Most importantly, consent under the Land Drainage Act for any structures that you're putting in stream channels or in ditches or in ordinary watercourses. Working in main rivers, you require the same type of consent from the EA. To fell trees and obtain your timber, you may require a felling consent or a felling licence. So it's worth talking to the Forestry Commission Woodland Officer for information on that. You may require a derogation to work on fields or land covered by other agro-environment schemes. If your earthworks are large enough, you may require planning permission from the local authority. Clearly, one of the main aims of putting in place natural flood management is to reduce flood risk. But another aim and a deliberate outcome from our work is the benefits for wildlife, for biodiversity, habitat and water quality, providing shelter for crayfish, trout and lamprey. The woody debris itself eventually rots down, and it's a major source of nutrients and energy. So the wood will become colonised by fungi and invertebrates, and as it decays, we find underneath those structures huge populations of shredding invertebrates, shrimps, fly larvae that will break that wood down. And of course, as we deflect water out of channels and we create wetter areas of ground, with wetness tends to come a richer diversity of plants. And so providing these wetter areas is a real boost to the biodiversity of a catchment.
It's quite a good principle. If things are already down nearby or across the stream, then of course use those as a good basis for your structure. And you can see on this one, it's already being colonised by ferns, lower plants, mosses, tons of invertebrates.
The version of natural flood management that we are implementing in Stroud is really a form of biomimicry. What we're doing is mimicking and copying what we would expect to happen within a wildwood, an unmanaged woodland system, where trees, logs and branches would over time fall into the watercourse and would form these structures. We know that there are other ways of attempting to make these structures naturally. Beavers, for instance, would potentially achieve a similar structure. But we also know that the vast majority of woody material in streams in wildwoods is there through processes of decay, windfall, and simply trees dying of old age. That's the natural process that we are attempting to mimic. Trees are really the engineers, in this case, of streams and watercourses. They deflect flow, they alter the way the water moves through the landscape. That's the effect we're trying to achieve in the Stroud Rural Sustainable Drainage Project.